So this time we are going to learn about convolution neural networks, right? And we talked about something known as edge detection. So what did we say about edge detection? We said that edge detection was one of the ways in which we could extract features from an image. So features from image. So what other features can there be? So we have edges, we have corners, and we have many more things that we can actually extract for images. Now there are other things also, and I'll show you all of this, obviously what the features were extracted, but I showed you a very basic operation of convolution. So if you remember what it was like, it was an image in this format which was a 6x6 image, and then we had a convolution of 3x3 Sobel edge detector. What kind of edge detector was this? It was a horizontal edge detector, right? And we got a 4x4 output, and this output actually showed us where the edge exactly was, right? So that was the way of identifying an edge. What I told you is this is also known as kernel or filters. So we had a specific value of +1, +2, +1 followed by 0, and then -1, -2, -1. So this was how our edge detector looked like. So if we change these values, then the new filter that will be formed, let's say change the values to 3, 4, 6, 1, 0, 9, anything, okay? So if we change this value to something else, this filter might be able to identify some other feature of an image. So basically it is the features that are identified using different filters. So these values of filters are the trainable parameters here. This is where we learn the values. So changing the value of the filter helps us understand different values of the feature. So this filter will now be convolved with the same image to give us new features. So that is how we learn about different features. Now once we learn about the different features, then we can actually identify the object or the thing that is for classification, a task or something. So let's say we have a dog here. So what are the features that can be learned? Well, you can learn about let's say pointy ears, then let's say tongue sticking out, 2 eyes, and all these features can be learned. Once all these features are learned, and once we can extract these features from an image, and then we can say, okay, pointy ears, tongue sticking out, and 2 eyes. Okay, so this has to be a dog, and so the convolution neural network can then identify, okay, so this image is that of a dog. So in that way, what is happening is basically it is able to identify the different features, and from those features finally we are able to identify, okay, so this is an image of this particular thing. So hence we use convolution neural networks. Okay, so now before I go there, in the last time we discussed about edge detection, right? We talked about the horizontal edge detection. So these are some of the images in which edge detection has worked. So here you have this flower, like you can see here this part here, this is a vertical line. So this is a vertical edge detector that has been used here, and you can see here. So the thing is, this is very dark, this is very light, the contrast is very high, hence this here is a very dark thing that has been formed, right? By the way, if you turn this horizontal edge detector by 90 degrees, you will get the vertical edge detector. So how does this look like? So we have +1, +2, +1, 0, 0, 0, -1, -2, and -1. So this is our vertical edge detector. So these are some of the filter values that we know because they are used to identify the edges. Now a few changes here and there, tweaks here and there, we'll be now able to identify even diagonal edge detectors and different edge detectors. But it is not up to us to understand what numbers and which combination of numbers will be able to identify a particular feature. It is for the model to learn on its own, identify the features, and then say, okay, so this image is the image of a car. Okay, so first let us talk about how an actual image looks like. Now these are all black and white images, so they do not have these RGB channels. So this is just a height and width. In the same way we had MNIST, right? We did not have any RGB channels in there. So we had height and we had width, but that was all. So now here, this is an actual image. So we have a red channel, a green channel, and then a blue channel. So this is a 4 cross 4 cross 3 image. So it has 4 pixels as the width, 4 pixels as the height, and 3 channels as the width. Okay, so now why I am introducing this is because we will understand about convolution in 3-dimensional images, right? So that means we will take different colors also into consideration. So we will understand this, and there are a lot other terminologies. This time we will not understand about how this works specifically on edge detection, but we will learn about convolution as a whole, how this works, right? Convolution as a whole thing, each and everything, and what happens, different terms and everything. So yeah, so let us go back and understand this. So we have an image, a 6 cross 6 image, height of 6 and width of 6, right? You can see that, you can count, nothing much. This is a convolution sign I was talking about. This is a filter or a kernel. Here you can see the values are different from a edge detector, right? So this is not used for finding edges, this is used to find some other feature. So we will be convolving this with the input and we will be actually finding the results. So what are the parameters? So we have size. Size is represented by F here, meaning short for filter. The size is 3. See, you have 3 cross 3, so size 3. So stride and padding, for now let us just leave these two. We will not be understanding this for now. We will come back to this later. So right now we have a size of 3. We will be keeping this here in the input. So now let us go back and understand once more about convolution. So I know you have already studied and understood this in the edge detection. The reason why we are doing this again and again is because it is very easy to get confused when simplicity decreases and you get it more and more complicated. So that is why it is very important to go and understand this. So how do we start this? We first place this filter over here. That is just for our understanding. We may not even do it, right? So we have 1, 0, minus 1. Then we have 1, 0, minus 1 again, and 1, 0 and minus 1 again. So what will happen once we have placed it is, we will multiply the input value with the value of the kernel that has been placed, right? So we will multiply 4 with 1 here, 4 with 1, what do we get? 4 plus 9 with 0. So 9 with 0 you have multiplied, you are getting a 0, plus 2 into minus 1, that gives you a minus 2 here, plus 5 into 1. So this gives you a value of 5, plus 6 into 0, so 0, plus 2 into minus 1, minus 2, plus 2 into 1, 2, 4 into 0, 0, and 5 into minus 1. So that is minus 5. So all this gives out an output of 2. So you have the value here 2. In the next part, what we will do is, we will now see this part is filled, but we need all these other values, right? So we will shift this by 1 pixel to the right, and now we will use this part here, and we'll place our kernel or our filter in this part and find the values. So now the output that we will get will actually fit here. Okay, so you have this again. So the same thing is here. This time this has shifted to the right. Okay, so now you have 9 into 1, 2 into 0, 5 into minus 1, 6 into 1, 2 into 0, 4 into minus 1, 4 into 1, 5 into 0, 4 into minus 1, and you add the whole thing together to get a value of 6. So you had 2 already, you added 6 here. We will shift this again one more time by 1 pixel. Right? We shifted it again. We will multiply the whole thing again, we will get a value here, then here, and so on until the whole thing gets filled up. Okay, so now we know how convolution is actually happening. It is not very difficult from multiplying this weights into x plus bias. So in one way we are actually multiplying the weights. If we remove this weights with, let's say, a filter, so in that case we are multiplying the value one by one to x, which is the input, and then we can obviously add a bias to it. That is no big deal, right? So I know there might be a lot of questions, so let me answer things slowly one by one so that you can actually understand stuff. So the very first question that came into my mind was, okay, so you have an input of 6 cross 6. I am using a filter of 3 cross 3. I am getting an output of 4 cross 4. So how is this happening? Like, is there something that controls this output value, or why can we not get 6 cross 6 as output? Like, why is this a specific number that is happening? Okay, so now we come back to stride and padding. So one thing that you need to understand is, it is using stride and padding that we actually control the output or the size of the result, right? Size of the feature that is extracted. How does that happen? So let us first talk about stride. So what is stride? This whole thing that we are doing, we were here and then we moved by 1 pixel. This is known as stride. So in this way we are moving by 1 pixel. In the down way again we'll move by 1 pixel, right? You moved here by 1 pixel. Then in the same way you will move here by 1 pixel. Again one more time to the right. Then you will move downwards by 1 pixel, right? So 1, 2, 3. Now this will be the new place. You have moved downwards. There is one more place that you can move it one more time downwards. Right? So we have once here this part, then we have this black thing, red thing, and then the yellow one. So we are moving downwards, but we are shifting them by 1 pixel. So we were here, then you shift by 1 pixel downwards, you are here, again shifted by 1 time, and finally another time. Okay, so this shifting by 1 pixel is known as stride. Since we are shifting it by 1 pixel, the stride is 1. Stride is basically moving forward. You know what stride means, right? Stride means like if you are here and then you take one step, so this is one stride. So in the same way, since the filter is also shifting by 1 step or 1 position, so that is 1 stride here. Here, see here, you had this here. You started with the filter being put in this place, right? Now in this case, what you are seeing is, I am not shifting this by 1 stride. I am shifting it by 2 pixels. So the stride here comes out to be 2. If I shift it by 3 pixels, so where will my output be this time? So I'll shift it by 3 pixels. So here. So this is where this will start with. So stride basically means the number of pixels you are shifting by. No big deal. Easy. So if I am shifting or I am having the stride of 3, in that case what will happen is, you will have this here, This was the initial position. Shift by 3 pixels. So 1, 2, 3. So the next time it will start from here. The kernel will be placed here. If we are shifting the stride by 2, in that case, you have this here. Very beautifully. Nice, nice. Then you are shifting it by 2 pixels. So 1, then 2. And now here you have the next filter. Cool. So that is what stride means. Now here you can see automatically, since this can be accumulated only 2 times, we cannot have one more time the kernel. So we have one here and then one here, right? Now if we shift by 2 times again, so we had 1, 2. Now here we have again 1, 2. So the third time it will be placed here. But oh, we have only 2 pixels here. We do not have another third pixel here. So we cannot have another value. So hence our result is 2 cross 2, because it can be shifted only twice if we have a stride of 2. Hence you can see the size of the result gets changed. The size is now 2 cross 2. The multiplication will be the same, you just have to shift it. So in that case, you'll have it here, you'll multiply the whole thing with this here, same. You'll shift it by 2 and now this will be the new one, this thing here. So this will be the new one, new place. Now in this place again, you will multiply all the values with the filtered values, convolute them, and then you'll get the final output result here. You cannot shift it one more time because now you have just one output left. You need to have at least 2 to actually find the result. Hence the stride is 2. So the size gets changed. Now the next thing is padding. So padding means basically you have the input here. You add one more layer outside this whole thing, like a border or a frame, to the image, right? So I am adding one layer of zeros outside. So the actual image is 6 cross 6, but since I added one more layer, now the actual dimension of the image is 8 cross 8. So since I am adding one layer of zeros outside the actual image, my padding becomes 1. So in that case, what will happen is, now we will start putting the filters from here. Now this whole thing will be taken as an image, nothing else. So our image has just increased, so we will do the same thing again. So our image will be taken from here. Now if we have a stride of 2, in that case what will happen? You have the 1 pixel here, the 2 pixel here. So the next time your filter will be placed from here. You have 3 here, here. Yes, your filter is placed. If we go downwards, what will happen? 1 pixel, 2 pixel. So this time it will be placed from here. So this is where we will place the filter, we will convolute, and we'll get the answer for this place here, we will get the answer here. For this one here, we'll be getting the answer here, right? So this is what basically we are convoluting and everything, and you're getting it. Now the actual dimension is 8 cross 8. So what we were having is, see, when the stride was 2 and padding was 0, we were getting a size of 2 cross 2. Now the stride is still 2, but the padding is 1. So in that case, we are getting an output of 3 cross 3. So how is this happening now? So we know what are the factors that are required to change the values. Okay, and also there is one more thing I totally forgot to mention. So padding itself is of 2 types. So in terminologies you will find 2 things. One is valid padding. That means no padding. No padding is known as valid padding. And then there is another padding known as same. So in that case, what happens is, it gets padded as many times as required so that the input image dimension is the same as the result dimension. So that means if we want a result of the same dimension as the actual image, so our actual size was 6 cross 6 and we need the result to be of 6 cross 6 again. Okay, so in that case we will pad, let's say one more 0, or how many 0 layers are required, that will be padded in itself so that our result is of 6 cross 6. So why is this needed? this same padding is required is because sometimes what happens is here we are actually losing some of the value. This image was 6 cross 6, the output is coming to 3 cross 3. So we have actually lost some value, some information of the image. We don't want that to happen. We want the dimension to remain the same. In that case, what we do, we use a padding of same. And then we also have a valid padding, which means the padding, there is no padding. The image is this, you have the filter here, you just multiply it without having another layer. Okay, so that is the whole thing. Now, how are we getting to these values, right? 6 cross 6, 6, 3 cross 3. How am I actually getting these values? So, we have this formula. This formula is basically used to describe what will be the value of the result. So, the value of the result, a convolution, is equal to input image dimension, this is basically input image dimension, plus 2 into padding minus size of filter divided by stride size plus 1. So that is how you are getting the value. So that means the result is, let me write it properly, input size dimension, which was how it was written, it was right, I suppose written in the form of n, right? N, yes. So you had n plus 2 into padding minus f by s, which is stride, plus 1. So this is how you are getting the dimension of the result. Okay, now you might be wondering why are there these brackets. So this basically denotes this is math.floor. That means the smallest value. So what that means is, sometimes what happens is, here like in this case, when you are having a stride of 2, you cannot increase, okay wait, here. So you had a stride of 2, right? So in that case you had first this part, this blue part, then you shifted it by 2, you had this black part. Now 3. Now again if you shift by 2, so you have 1 here, 2 here, so you have to start from here, right? But you have only 2 values, you cannot have a third value. So math.floor basically means that the floor, that is the nearest value. So if you get a 2.3 value, so the nearest value in the lowest part, so this will be equal to, so rounding off basically to the nearest number but in the lowest part, not in the higher part. So this will be equal to 2. So that means even if you get 2.7, this will be approximated to 2, right? That is math.floor, and that is why this is used. So this is the whole thing basically. So now let us get back to this question. So for in this question where we have an image dimension of, wait, let me clear this. So let us write n plus 2p minus 1 minus f by stride plus 1 is the result, right? Now for this equation where we want a padding to be same. So in that case what will be the actual number of padded that will be required, right? So we have an input dimension of 6 plus, we don't know the number of padding, so 2p minus, what is the size of the filter? 3. So minus 3 divided by stride is 2. So stride 2 plus 1, right? Now the result has to be, because the padding is same, so the result dimensions are the same as the input dimension. So this is equal to 6. Basic mathematics, right? Nothing much. So what will this come to? So you can calculate this. 6 equal to 6 minus 3 is 3 plus 2p by 2 plus 1. So this is 5 equal to 3 plus 2p by 2. So 10 equal to 3 plus 2p. 7 is 2p, and so if you divide, it's 3.5, that means 3. So you have to have a padding of 3. So you have one padding, you have to add 2 more layers of padding to actually get this dimension. Okay, so that is basically what the whole thing of same padding and valid padding mean, right? Then we got how to use this. There is this formula, and I say right now, because just go and learn it, just basically learn this, because you are going to need it many times. You will actually require it to get the value of each thing. Okay, so this is how this is how stride and padding actually control stride, padding and the size of the filter actually control the dimension of the result that we are going to get. Okay, now let us get back to the second question. The first question was how this size is changing, right? My second question is, see, right now what we are dealing with is, well, all this is flat. That means we have just 2-dimension here, 2-dimension images. But we always talked about 3-dimension images which had RGB channels, right? So how are we to deal with such problems? In that case, what happens is our kernels are no longer flat kernels. So our kernels themselves will have some depth to it. So in that case, this kind of Rubik's cube looking thing will be our kernel. It will have 3 channels itself. Because why 3 channels itself? This 3 channels is to complement the 3 channels of the image. So our kernel will no longer be flat, we will have a 3-dimensional kernel itself, right? So that is how we will be handling such kinds of problems. Here you can understand more here. So now here we have height, width and the number of channels. Height and width is 6x6, channels 3, red, green, blue, red, green, blue. So what will happen now in this case is our filters itself will have 3 different channels. So we'll have red channel, green channel and blue channel. So the red channel of the filter will convolve with the red channel of the image. The green channel will convolve with the green channel of the image, and the blue channel of the filter will convolve with the blue channel of the image. So you will have red channel of the image convolving with the red channel of the filter plus green channel of the image convolving with the green channel of the filter and blue channel of the image convolving with blue channel of the filter, and they all get added up to get our final result. So our result, even though we are multiplying 3 different channels with 3 different channels of the filter, we will still be getting a 2-dimensional result. Okay, so here you can see what is happening is, here you have the image, it has been broken down into 3 channels, right? So we have this red channel here, we have a green channel here and we have blue channel here. So now this is the red channel of the kernel, right, which is being convolved with the red channel of the image. Then green channel of the kernel being convolved with the green channel of the image. The same way, the convolution will be the same as we were doing for 2D flat images, right? We had this, we were convolving both and we were getting the values. The thing is going to be the same, it's not going to change. So once the convolution is done, we get the values, right? So this value we are getting here, this value and then this value, all these we are adding. So this is a GIF obviously, so the value keeps changing because the filter keeps shifting. What is the stride here? If you will see, the stride is 1 and we have 1 layer of padding also, right? So this gets multiplied. Once the convolution is done, all the 3 values get added up. We also add a bias. Now this bias here is given as 1. Obviously this bias is a trainable parameter and it will be trained for depending upon our problems and our values, right? So once all of this has been done, they get added together. So it is basically again this weights into x plus bias. Once this is done, we get the final output. Our output will still be a 2D image. Okay, so this is what is happening in this whole thing. Now getting back here, now I'm pretty sure this is more clearer to you because of the GIF. So you have this, it is getting multiplied 1 by 1, 1 by 1, 1 by 1. Convolution is done the same way. The convolution is in the same way. It's just after we have convolved all of these 3, we will add all the values and we will add 1 bias to it and we'll get the final result. Okay, so what next? Okay, so one thing that you should know is, okay, this is how we use the filters for a 3D image and get output. So this is one, so this whole thing, the whole result gives us one feature of the image, right? So we were using edge detection. So edge detection was one feature of the image. I am not sure, let's just say this whole filter, these numbers of the filter are used to identify the corners. So we got one feature, that is the corners of the image, through this whole filter and convolution thing. So this is one feature. But what if we want to increase the number of features? We don't want just one feature, we want one convolution network, so that it is able to identify both the features and all the features that include edges, corners, points and everything in the image itself, right? So we obviously need more than one filter, because one filter may be able to identify edge. We need another filter that is able to identify a corner. We need another that is able to identify points and many more of such features, right? So that is why we increase the number of filters. Now we have this input, we have these filters, right? This gives a 4x4 output. Then we again have one more filter. So the filter values are different. If you will see here, this filter, let's say this is able to identify edges, so this might be able to identify corners. So now we are getting here again a 4x4 output. Now the actual output, since we have used two different filters, will be 4x4, and then what we will do is we will concat both these outputs and 4x4x2. So we have two different outputs. Here you have the features that are identified after detecting the edges. Here you have the features that are identified after detecting the corners, right? So one thing that you need to understand is the number of filters will give us the depth of the output, right? So you have to choose the number of filters accordingly. So just to revise back, we understood about convolution when we had a two-dimensional image, right? Without RGB channels, we understood that. We understood about filters, and then we understood how this was working. Then we had one question. The one question was, what happens and how does the size of the result keep changing? Okay, so we had that question. So then we understood about two different terminologies, that is strides and padding. So then we understood the formula that is used to identify us what the size of the image will be, the dimension of the image, right? By the way, padding itself is of two types. We have valid padding and we have same padding. Valid padding basically means that there is no padding. Same padding means we have the input, this needs to be the same as the output. So that means our padding needs to be the same in such a manner so that the input is the same as the output. Once we have done the padding, we have the formula for the result. Then we understood how this works for 3 channels or 3D images, right? So we had our red red channel multiplied with the red channel of the filter, convoluted with the red channel of the filter. In the same way we had green and we had blue, and this was ultimately added with and then added with the bias, and we had the final two-dimensional result. So once that happened, we understood, okay, so one filter is used to identify one particular feature of the image. So if we need more features, we need more filters. So in that case, we need to increase the number of features. What we understood one more thing was, if we increase the number of filters, the number of features is going to increase. One filter gives one feature, so the number of filters will give you the number of features. So that is the whole thing that we understood. Now the next class, what we will understand is about something known as pooling layer. We will understand about normalization layer, and a few more things about convolution neural networks and the whole structure as is. So right now we are just learning parts of it, right? Like if we have to compare this to a multi-layered perceptron, what we might be learning right now is you have these inputs and how this is being passed through an function to give you the output. So we are just learning about one neuron. We have to understand the whole structure as one thing, right? So that is what we will be understanding. So thank you, that's it for today. Nice day and keep learning.